What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to talk about limits at infinity, which are limits as x approaches infinity or as x approaches negative infinity. So here's a graph just to show how we think about this. A limit at infinity means as x gets bigger and bigger, what's happening to the y values? Are they approaching some number, like they are in this case? The y values are getting closer to 1 as x gets bigger and bigger. In that case, the limit exists and equals that number. If they aren't approaching any particular number, usually that's because they're increasing or decreasing without bound, then we could say the limit does not exist, or we could be more specific and say it's infinity or negative infinity because it increases or decreases without bound. Similar thing where we're thinking about negative infinity, we're thinking about x values getting smaller and smaller and smaller, what's happening to the y values. Let's look at one more example. These are both rational functions. This time I give you the defined function as well. What's the limit as x approaches infinity? As x values get bigger and bigger, we're tracing the function, and we're looking at the y-axis, thinking about what happens to these y values, and they are getting closer to 3. And the same thing is happening in this other direction as x gets closer and closer to negative infinity, so smaller and smaller. Okay, so we've dealt with two rational functions, and we hopefully see this correspondence between these limits at infinity and this end behavior of a rational function, more particularly this thing we call a horizontal asymptote. Here this line y equals 3, here this line y equals 1, and it turns out there is a correspondence between these things. Limits at infinity correspond to horizontal asymptotes. Okay, so the line y equals L, this is actually a way to define what a horizontal asymptote is. The line y equals L is a horizontal asymptote of a function if and only if either the limit as x approaches negative infinity of the function equals L, or the limit as x approaches positive infinity of the function equals L. Only one of these two things actually has to exist, right? Or be true. Notice that word or, that seems kind of weird, but there's actually a really common example we know where only one of these two things happens, and that's an exponential function. So this is an example of an increasing exponential function. This has what we call a horizontal asymptote. If it's the parent function, it's y equals 0, and that only happens as x goes to negative infinity. As x goes to positive infinity, it increases without bounds. So only one of these two things need to be true for us to call it a horizontal asymptote, but this is a way to define horizontal asymptotes. And so since we're relating limits at infinity to horizontal asymptotes, we can actually think back to like algebra 2 pre-calculus, especially since we're dealing with rational functions. Hopefully at one point we learned these rules for determining whether a rational function has a horizontal asymptote and what that horizontal asymptote is. So they all have to do with the degree of the numerator and the degree of the denominator and comparing those two things. So if the degree of the numerator is bigger than the degree of the denominator, then the function has no horizontal asymptote. If they are equal, then it does have a horizontal asymptote, and it's the line y equals the ratio of the leading coefficients. And if the degree of the numerator is less than the degree of the denominator, then there is also a horizontal asymptote in this case, and it's the line y equals 0. So we're going to quickly dive into some examples and hopefully try to understand why these rules work by thinking about limits, by thinking about what happens as x gets really, really big. So let's look at these first two examples. And it turns out as x gets really, really big, we can think about the rates in which the numerator and denominator are growing. So this first example, as x gets bigger and bigger, and I'm talking really big, 1 billion, 10 billion, 100 billion, these two quadratics, right, if I just ignore the 3 over 2, are growing at very similar rates. They are actually getting closer and closer to the same value. So in other words, this entire fraction is getting closer and closer to 1. So we have similar growth rates here. They're getting closer to 1 as x gets bigger and bigger, which just leaves us with that 3 over 2 out in front that gets multiplied. And this aligns with our rule, right? The degrees are the same, so the horizontal asymptote is the ratio of these leading coefficients, which is y equals 3 over 2. And so since that's the horizontal asymptote, that's the limit, and it actually wouldn't matter if we approached infinity or negative infinity. These horizontal asymptote rules for both. When there is a horizontal asymptote, it works from both, as we saw with these examples, right? When these nice rational functions have horizontal asymptotes, that's the end behavior on both ends, toward infinity and negative infinity. That's not the case with more complicated examples that we're going to see in a future video. So here we have 3 over 2, and so why does this limit go to 0? Because that's what we saw with our horizontal asymptote rule. Now the degree of the numerator is less than the degree of the denominator. The horizontal asymptote is the line y equals 0, which means this limit is 0. And again, we could think about growth rates. Now the denominator is growing faster than the numerator. What happens when a denominator grows faster than a numerator? Well, you can check this out yourself. Take something like 2 over 2 and square the top but cube the bottom. And look what happens to this thing. Let's do it one more time. Square the top, cube the bottom. Oh God, what is 8 cubed? 512? Yes, awesome. And imagine if we went again, we're just getting really, really small. The value of the entire fraction is getting really small and closer to 0. And this is true if there's a negative coefficient. That's true as well. We're just getting closer to 0 from the negative direction. In either case, really, the coefficients doesn't matter. This is 0. It's getting closer to 0. And so now let's look at our last case where we have it flipped, and now the degree of the numerator is bigger than the degree of the denominator. And we said that this meant that the function has no horizontal asymptote, which means it's doing one of two things as x goes to infinity. Either it's doing this and just getting bigger and bigger without bound, or it's doing this and getting smaller and smaller without bound. So we could just write this as dne, and how we could understand this is that now the numerator is growing faster than the denominator, so take these fractions and flip them, right? Now this time cube the numerator and square the denominator, and we have a thing that's just getting bigger and bigger. But what if we want to be more specific, which is what I always recommend? If you can write a limit as an infinite limit by describing it as either infinity or negative infinity, then you should, because it provides more information about why the limit does not exist. So although this is a correct answer, I want to push us to be a little bit more specific and think about, could we write this as infinity, or could we write this as negative infinity? And maybe you have some good ways of thinking about this. Maybe you're looking at the coefficients, right, both being positive and thinking about things like that. And there's one particular way that I like to think about it because it always works and it works really well. And it avoids some of the faulty intuition I see students run into when there are negatives and that sort of thing that we're going to see with actually an example I'll give you. And that's this intuition here, which is the outputs, the y values of a function, of a rational function, can be approximated by the ratio of the leading terms for really big values of x. So what that means is like x equals a billion, 10 billion, 100 billion, right? What happens to the output of this function is that it gets really, really close to just the output of the two leading terms, the ratio of those terms. So this is how it's often written, and this is how Sal Khan will write it. If you've ever watched his videos, he'll say this thing could be approximated by this when x is really big. And sometimes he writes that out. I'm not going to in this case. I'm just going to say it. When x is really big, this can be approximated like this. And this is another way to think about it. Really, these are just two different ways of saying the same thing, which is that this means the end behavior of a rational function is the same as the end behavior of this new function that we define by looking at the ratio of these leading terms, these fastest growing terms. So again, the leading terms, I'm looking at the biggest exponent in the numerator, the biggest exponent in the denominator. I'm looking at that new function, and now I can actually cancel this out. Let's see, am I removing a discontinuity by doing this? I am, but that's okay. It doesn't matter because x is approaching infinity. It's getting really big, and we remove these discontinuities. Like, what did we just remove? Now it's defined at 0. Before it wasn't. So we can add a qualifying statement here that these two things are equal for x bigger than 0, and that's totally good and totally fine. And we're allowed to do this because x is approaching infinity. We want to think about what happens at a billion, 10 billion, 100 billion. We don't care about what happens at 0. Awesome. So what does this function look like? Well, I like to write it like this, 1/2 x, because then it lets me think of the end behavior, which is a positive sloping function like this. It's linear. So as we go toward infinity, it blows up to infinity as x approaches infinity. And as we go toward negative infinity, it goes down to negative infinity. So we could think about that limit as well. Hopefully that makes sense. When we have these examples, if we want to write infinity or negative infinity, we can. We just think about this different function that's the ratio of the leading terms. All right, let's get some practice. Hopefully I didn't ramble too much. Here's 3 examples. If you're already feeling confident, pause the video now, pull out a piece of paper, try these on your own. All right, let's jump into it. First example, I'm using my horizontal asymptote rules. And I know that the degree of the numerator is 4, the denominator is 2, and that means the numerator is growing faster than the denominator. So this thing is either going toward infinity or negative infinity. The limit doesn't exist. The function doesn't have a horizontal asymptote. But let's write it as either infinity or negative infinity by doing exactly what we just did, thinking about this ratio x to the fourth should be in the numerator over x squared. And this is equal to x squared for really, in this case, we want to think about really small values of x. So for x less than 0. These two things are true. This is undefined at 0. This is defined at 0. We removed that discontinuity, but that's okay because we can just put that condition and think about what happens as x gets smaller and smaller. All right, what does the end behavior of this function looks like? Well, that's a pretty easy one. As we go right, we go up. As we go left, we go up. So this is an example that I like to give of why I really like to use these rules, because so many kids will say the limit as x approaches negative infinity, positive number, so this is negative infinity. But it's not, right? Because look at the ratio. The difference between the biggest terms is x squared. And that actually goes to positive infinity as x goes to both positive infinity and negative infinity. The y values increase without bound. So this one we actually want to say positive infinity. And that's why I love applying this rule we just talked about here as a way to think about these, because it just works so consistently every time. We avoid those mistakes. Awesome. All right, let's jump into the next one. Degree of the numerator is 3. The degree of the denominator is 4. 3 is less than 4, so this goes to 0. That's the horizontal asymptotes, y equals 0, so that's the limit. And it doesn't even matter if x is going to infinity or negative infinity. That will be the limit in each case. It also doesn't matter what the coefficients are. Boom, it's still 0. This is an easy example. Next example, as x goes toward infinity, well, now we have degrees that are the same. So what's the ratio of the leading coefficients? Well, there's just a negative up front, so I'm going to write that as negative 1 over 4, boom, negative 1/4. You could also write the negative out in front, totally fine. Negative 1/4, that's our limit. And again, that would be the same if x approached negative infinity. All right, another set of examples. If you didn't pause last time, seriously, this time, pause, check your understanding, press play to check your answers. All right, let's go from top to bottom. This one I love to put on tests. This is my check. Are you going too quickly? Are you moving too fast? Because kids want to just write down 3 and move on. Why is that wrong? 3 over 1. Well, these aren't the biggest powers of x, right? What's the degree of the numerator? It's 2. The degree of the denominator is 3. 2 is less than 3. The denominator is growing faster than the numerator. The entire thing's going to 0. So these are not in standard form, written from biggest to smallest power of x. And sometimes that happens. And you got to make sure you're paying attention, you're reading all the way through, and you're not just zooming in and looking at the first 2 terms that appear on here. So here we got 0. And the next one, what do we got? Power 2, power 2. Degrees are both 2. They're the same. So I'm going to take the ratio 4 over 2, which is equal to 2. And that's the limit. And it doesn't matter whether we're going to negative infinity or infinity. We're dealing with rational functions. In these cases where these do have horizontal asymptotes, it's actually pretty easy. And finally, let's go down here to this one. What do we have? Negative 3x cubed. That's the biggest exponent up here. Okay, so degree 3. And then degree 2 down here. Okay, so top is bigger, so we know it's going to be dne, and we can either write it as positive or negative infinity. So let's write dne or, and we're going to put our final answer here after we investigate these values of this function. I'm going to switch colors. The values of this function can be approximated by the ratio of the leading terms, which is what? Minus 3x to the third power in the numerator. And in the denominator, we got to, again, be careful. Make sure we're paying attention. Negative 5x squared. All right, hopefully we see how I'm getting that. That's the biggest term. That's what we want to take the ratio of. So the outputs of this function can be approximated by this expression when x is really, really big or really, really small. And so now we can do what? We can cancel some negatives. We can cancel 2 of these x's. So we can write 3x over 5. So I did 2 things at once. Minus, minus, right? Got rid of those. And then canceled 2 of these x's. And again, we got to keep in mind, this is only true when x is not equal 0. So I'm just going to add this for x greater than 0. And I'm just writing that to make sure you understand it, that when we are canceling this stuff, we are technically changing the expression. So when I write this equals, if I don't write anything else, technically what I've written is wrong. These are not equal for every value of x, right? So I'm adding that condition just so I don't have something on my screen that's wrong. Hopefully you respect that. All right, what does this do? What's the end behavior? Well, it's a linear function. It has a positive slope, so it's going to look like this. As x goes to infinity, the y values get bigger and bigger. They increase without bound. So we can either write dne or be more specific and write infinity. All right, here's the final thing we're going to do. The final thing we're going to do is we're going to look at some limits at infinity analytically. Ooh, that was kind of a bar. Limits at infinity analytically. All right, anyway, let's jump into it. This is something your professor or instructor or teacher might ask you or expect you to do. I know I want my students to do this at least once, which is find these limits analytically by dividing the numerator and denominator by the same thing and actually using limits to find the end behavior of this function, right? So using our rules, we could just say 1 over 1, that's the limit, it's 1. But let's actually divide, and here's what we divide by. We find the biggest power of x in both the numerator and the denominator. So we look at the entire numerator, the biggest power is 2. The entire denominator, the biggest power there is 2. And we're going to divide both the numerator and the denominator by that biggest power of x that shows up, right? So for example, if the denominator had an x cubed, but the numerator only had x squared, that was the biggest power, then we divide top and bottom by x cubed, the biggest one. And the reason is, well, it's going to make it work out, obviously. And obviously we have to divide by the same thing. Otherwise it changes the value of this, right? We don't want to change the function. We want to divide by the same thing, top and bottom. Awesome. Here's what happens. It works like magic. This limit is equal to this limit. The limit as x approaches infinity of, what do we have in the numerator? X squared divided by x squared, that's 1. Plus 3 times x divided by x squared. Well, let's see. One of the x's cancel. I'm just left with this. And then plus 2 divided by x squared, I can just write that as a fraction. 2 over x squared. Okay? Now let's look at the denominator. X squared over x squared, that's 1. Minus x over x squared, that's going to simplify to 1 over x. 1 over x. Awesome. And then let's see, minus 12 divided by x squared. And so these two limits are the same. Again, sometimes we may introduce or remove discontinuities when we do stuff like this, but we're considering what happens as x goes to infinity, so we don't really care. These limits are the same. They are equal. And now look what's really cool is I see a bunch of stuff that goes to 0 as x goes to infinity. Anytime we have a constant over some power of x, right? Boom. Well, assuming it's a power of x that's bigger than 0, right? This goes to 0, okay? 3 over x, as x gets bigger and bigger, 3 over 10, 3 over 100, 3 over 1,000, going to 0. This goes to 0. This goes to 0, right? All these pieces go to 0 as x goes to infinity, and so what we're left with is 1 in the numerator, 1 in the denominator, and so the limit is equal to 1. So I showed you one example of how to find these limits analytically. And again, that's the strategy. We're dividing numerator and denominator by the biggest power of x. We're ending up with a bunch of stuff that goes to 0. And then whatever we're left with, that's going to be the limit. And we're going to do this and make it a little bit harder in the next video where I go over examples of finding limits of functions that aren't rational functions, that have square roots and exponentials and all that stuff, where we kind of have to understand this method to do those. But hopefully you enjoyed this video. Hopefully it helped. If you did, hit like, leave a comment with questions, subscribe, do all that stuff. But most importantly, keep flexing those brain muscles, and I'll see y'all later.